So for chapter one here, actually week 1 here, we're going to be chapters 1 and 2, but for chapter 1, just a little bit of an overview of statistics, what some of the vocabulary words mean, and why are we studying statistics. So the first question is, what is statistics? Well, statistics is the science of collecting data, analyzing that data, and then drawing conclusions from it, whether those conclusions are just wanting to get a snapshot of what the characteristics are right now, or trying to use that data to either make a decision or to predict something coming up in the future. So why should one study statistics? Well, there are a lot of reasons. It basically is to answer questions. Like we said, what does the data look like right now? If it's a graph, and we can put it in a graph and look at that shape. Or to answer a question, can dogs help patients with heart failure by reducing stress and anxiety? How do we determine whether those dogs actually do have a real measurable effect? Or is it just an anecdotal effect? When people take a vacation, do they really leave their work behind? So does taking a vacation really reduce stress? It's just some of the examples of questions we can answer with statistics. So why do we study statistics? One is to be informed, to know what is actually going on around us. The media and other sources are going to put out all sorts of statistics and numbers trying to tell you what's going out, but in many cases there is a special interest there behind it, trying to convince you, sway you in one direction or another, rather than just giving you the information and letting you decide. So you need to be informed for a couple of reasons. One is so you know when someone is trying to mislead you with the numbers and the statistics, and two, so you can look at those statistics and make the decisions for yourself. So you'll see a lot of graphs and tables and charts that are presented to be able to evaluate, first of all, understand what those charts and tables are saying, but then to be able to evaluate whether they're misleading or not, to see if there's hidden information there or what the information there really means, and not just by that first impression, first appearance. Following a numerical argument. Somebody might try to convince you that product A is better than product B and display this, all this information that seems to prove their point. But can you follow that argument and see if there's flaws in that argument, or even if the argument itself, the whole argument itself is valid? Then understand the basics of how data should be gathered, summarized, analyzed, and to draw statistical decisions. We live in an age where statistics, especially with the electronics age, the ease of gathering statistics and applying it, everybody needs to have some understanding. Business decisions need to be made using statistics on a basis of actual numbers. Even in sports now, some football teams actually have assistant coaches hired to sit on the sidelines with tablet PCs running statistics, trying to decide, is it best to go for it or to punt on 4th down or things like that. So they're all around us, and any major decision, well-made decision, should be based on some sort of background information. To make informed judgments. That's just what we were saying there. We understand those statistics, and once we understand the statistics and what the history is of those numbers, then we can make a judgment of what do we do now or what do we plan for in the future. What are the patterns in that history, and how do we expect them to continue, and then how are we going to utilize that to make a decision? For example, if you choose a particular major, what are your chances of finding a job when you graduate? If you're picking a math major, what types of jobs out there? What fields are hiring? How many jobs are out there? How many jobs come available every year? You might pick a major where there's a ton of jobs out in the workforce, but nobody ever leaves those jobs, so jobs don't ever really become available. That's not necessarily a good choice if you're hoping to get a job in your field when you graduate. There might be other majors where there's not that many jobs out there, but there's a lot of people at retirement age and a lot of jobs coming available in a short period of time. So that might be a good choice. And then to evaluate decisions that affect your life. Whether those decisions are made by you or made by somebody else, Decide if that's a good decision, if it's something you wanna deal with, tolerate, or if you wanna try to go a different direction. For example, many companies now require drug screening as a condition of employment. With these screening tests, there's a risk of a false positive reading. Is that risk of a false positive an acceptable result? Or is it an acceptable risk? So again, is the need to make sure your employees are competent and capable when they come to work, does that outweigh the risk that you might accuse an employee of something they didn't do? So you need to balance that out and figure out how are you going to handle that? Are you going to, if you always offer a retest option when there's a positive, what are the chances of getting a second false positive on the same candidate? And things like that. How effective is that going to be? The next topic, the first big topic really in statistics, with statistical analysis is to understand variability. Variability means things are not identical to each other. In a perfect world, if we said something was 12 ounces, like a can of soda, every can of that soft drink would be 12 ounces exactly. But it's not a perfect world. So every can gets filled a little bit differently. You know, the machine that fills them, a little bit dribble sticks on the end of the spout, or that extra dribble falls into the next can, or air movement takes a little bit with it, or whatever, splashes out. Always little things that might affect that. So no, they're not exactly the same because of variability. Now, variability is inherent in any process, and it's actually universal. What we're looking for is processes where we can predict the variability, have a control on the variability. When the variability is by means that we cannot predict, that's when we have worries. So is that variability is what makes life interesting. It's also what makes statistics difficult, because in our statistical analysis, the big thing we have to account for is that variability. We can't just compare two numbers and say this one's bigger than the other, because we have to account for the fact that there's variability in both of those numbers. So how do we account for that when we make that comparison? So in this case, if we have two histograms, to the right displaying the distribution of heights of gymnasts and then the distribution of heights of female players. Which is which? So in many cases, you can just look at the display, the distribution of or the shape in this case of a graph, and figure out which is which. If you know one is gymnasts, which are typically shorter, and one is female basketball players who are typically taller, we see that this top one here, skip back, has more people in that tall range. So we would say that that is most likely our female basketball players. In fact, the shortest person is taller than half of the other set. So that set there with the smaller heights, 6 inches, 60 inches is 5 foot. Hard to imagine a gymnast that's 6'2", to be honest, but apparently there's a couple out there. That's obviously the gymnast in that lower end. So suppose you found a pair of size 6 shoes left outside the locker room. Which team would you go to first to find the owner of the tennis shoes? So it's referring back to these graphs here. Well, size 6 is relatively small. I would go to the team that has the smaller people. Height and shoe size tend to correlate. So the shorter athletes would tend to be more likely to have the smaller shoe size. So again, suppose a tall woman, 5'11", tells you she is looking for her sister. That should be she is looking for her sister who is practicing with a gym. To which team would you send her and why? Well, 5'11" is almost 6 feet tall. That's relatively tall. Being siblings, we would expect their siblings to be similar heights. 5'11" here is right there. There's only a few gymnasts that are taller than 5'11". Whereas up here, 5'11" is right there. A good share of the basketball players are taller than 5'11". To be totally honest, the answer they're looking for is to send them to the basketball team because basketball players tend to be taller. But this is a case where it all depends on whether that the person you're talking to is taller or shorter than their siblings. Oops, gotta go one more. She's looking for her sister. It doesn't say older or younger, so it's really hard to predict whether they're taller or shorter, but they're looking for you to go to the basketball team because 5'11" is at the upper end of that height distribution. And so you'd be looking for someone who is taller. So the process of analyzing data. First, we need to understand the nature of the problem. What is it telling us? What are the things that attribute to the variability in that data? It's important to have a clear direction before we gather data. What is it we're trying to find out? What are we trying to study? Partly because we need to define the population to accurately do anything with it. Decide what to measure and how to measure it. Sometimes it's hard we want to learn a certain thing, but that's not what we're measuring. It's actually a secondary characteristic that we're measuring in order to make predictions about what it is we're doing. So we need to carefully define what our variable is so that we can develop a proper method for gathering information on it. And then we collect data. There's a lot of things that are involved in this data collection process that we have to worry about, mostly making sure that we don't introduce any biases into it. So it's important how to collect the data because the way we collect it also will affect the methods that we can use to analyze it. Summarize data and perform preliminary analysis. So summarizing data, most of us have had data summary topics in other classes, finding mean, median, mode, stuff like that, making tables and graphs. Those basics are actually the first step to analyze the data to see if it's even worth going on into deeper analysis. Then to perform the formal analysis. So the formal analysis is where we really learn about the data, and this is going to be more complex, but we, with that background information, we now select the appropriate tool method that we're going to use to analyze that data. And then finally, to interpret results. No amount of data analysis does us any good unless we can interpret it and then apply that result to something or determine that result doesn't apply to anything. So suppose we want to know the average GPA of a high school graduate in the nation this year, or of high school graduates in the nation this year. We could collect data from all high schools in the nation. Of course, that would take a lot of time, and that is our population, is all high school graduates this year. But that would take a lot of time to gather that data from everybody. But the term that we would use, what we're describing there, all high school graduates, would be the population. So our population is all students who graduated from high school this year. So what is the population? Population is the entire group of objects or individuals that we want to learn about. So what do you call it when you collect data from the entire population? That would be called a census. A census is that attempt to gather information from every item or person in the population. So in this case, if we tried to collect information from every high school in the nation, that would be a census. If we didn't perform a census, what would we do? Well, a census is often very difficult to perform. Time and money are usually limiting factors because the population is usually rather large. And sometimes it's difficult to track down everybody in the population. So we take a sample. A sample is just a smaller group that is chosen from that population, so a subset from the population. But we can't just go and select any sample. We have to be careful how we go about that. So what would a sample of all the high school graduates across the nation look like? Well, We could pick some high school graduates from each state, each gender, each economic background, each ethnicity, etc. But how would we do that? How would we determine where to select them from? Well, once we have collected the data, what would we do with it? But we'll come back actually and we'll talk about how to select that sample later on, just so you know. So once we've collected that data, what do we do with it? Well, that's our analysis. We look at our descriptive statistics first. So we organize the data and summarize it using tables and graphs. So if the sample of high school GPAs that we collected contains 1,000 numbers, how would we go about organizing that? 1,000 numbers, if you just have a list of 1,000 numbers, you're not going to look at that and be able to comprehend it. You're not going to be able to take that all in. So we have to organize it in some way to make it easier to comprehend. So we create a graph or a table. So we need to create those tables and graphs. We first need to come up with ranges of GPAs so that we can divide them up. We're not going to display each GPA separately. We might calculate the average GPA. We might calculate the variability using the range. So how could we use the data from our sample to answer a question? So once we've gathered it and organized it, what are we going to do with it? So that's where the inferential statistics comes in. It involves making either a generalization from a sample to the population. Our sample had an average GPA of 2.8, so we're going to assume the population has an average GPA of close to 2.8. Or it might be used for making a decision. So in this case, we might say, based on our sample, if the average GPA for high school graduates was 3.0 on our sample, what generalization could we make? We would say that if the sample that we took had an average GPA of about 3.0, then we would say that the average national GPA for this year's high school graduate is approximately 3.0. We're just saying what we found in our sample, we're going to generalize that to our population. Again, that's assuming we took a good sample. And we haven't talked about taking a good sample yet. What's involved in that? Could someone claim that the average GPA for graduates in your local school district is 3.0? Can we generalize that backwards? If we say the national average is 3.0, does that mean each individual school district is 3.0? No. Our generalizations cannot go backwards like that. We can go from small subsets, small samples up to the major population if the sample was taken well. But going backwards from a population to a sample is not as accurate. And in this case, one local school district would not be a good sample. So we can only take generalizations from the population back to samples that were similarly chosen to the sample that we started with. Taking a whole school district is not similar to the random sample we started with. So be sure to sample from the whole population of interest. A single school district is not a good sample from the whole population of interest. So a variable. When we're doing these statistical studies, we are asking a question. Our variable, the random variable, is the answer to that question. So a variable is any characteristic whose value may change from one individual to the next. Suppose we want to know the average GPA of high school graduates around the nation. Again, define the variable of interest. Well, the variable of interest is the GPA of high school graduates. So is this a variable? The number of number of recs per week at the intersection outside the school. It would be a variable, but it's not our variable of interest. Data. So data is the values that we gather for the variable. Every individual in our population has a value for that variable. So we've narrowed it down to our sample. Every individual in our sample has a value for that variable. The data is the value of that variable for each of those members of our sample. So for this variable, the number of recs per week at the intersection outside, what would observations be? Well, 0 recs, 1 rec, 2 recs, and so on. So there are two types of variables we're going to look at. Categorical, sometimes called qualitative. The terminology means the same thing, but it gets interchanged depending on what textbook or who you're talking to. I'll warn you, I teach another class where in that textbook uses qualitative instead of categorical. So you might hear me flop back and forth between those two terms now and then. And the other one is numerical or quantitative. A number is a quantity. So that means the answer to that question being asked, our random variable is going to be a number. And of course, there's going to be breakdowns within each of those categories as well. Numerical could be discrete. The best way that I can describe discrete would be counted. Like the number of recs. There's 0 recs this week, 1 rec, 2 recs, 3 recs. You're counting those. You can't have 2.5 recs. And then there's continuous. Continuous, best way to describe continuous is measured. The height of a basketball player. Now in our example, we just went to the nearest inch, but we could go to the 100th of an inch or the 1000th of an inch. We could go to we can measure to as small of a unit as we want to, depending on the level of precision we want. So in continuous, we can measure to smaller and smaller units if we want. Or discrete, we're strictly counting items. Let's look at categorical variables a little more closely, the qualitative variables. This identifies a basic differentiating characteristic of a population. So anything where that answer to the question being asked puts you in a category based on a characteristic, that is a qualitative or categorical variable. Can you name any categorical variables? Well, I'm sure you can if you think about it. If you want to pause the video for a second and think, go ahead. I'll give you some examples here. Examples of categorical variables. Any yes or no question puts you in a category. Do you favor this proposed law? Yes or no? That's a category. Favorite color. That puts you in a category of people that like blue or red or green or whatever color. Other categoricals might be political party. What political party do you favor? Do you favor Democrat, Republican, or a third party? Puts you into a category. And there are several other categorical variables that we could think of. So numerical variables. Again, quantitative is the word we threw out there. These observations, they observe or measure numerical values about our items in our population. Because they're numbers, it makes sense to average them. The analysis of quantitative data is a little bit more versatile. There's a lot more things we can do with the numbers to analyze it, rather than just grouping it and summarizing it. And again, we said there's the two different types, discrete and continuous. Can you name any numerical variables? I'm sure you can name a lot of them. So again, if you want to pause the recording to see what you can think of, go ahead. I'm going to name some here. Height, we already said, is one. The time it takes to complete a task is another. Time is usually continuous. Number of classes that you're taking, that's numerical. Number of children that you have, again, that's numerical. And again, there are several others that we might be able to choose. Well, let's look at discrete numerical data here a little bit more closely. It has isolated points along a number line. In other words, they're counted. So usually a count of items, but you can have isolated points, 1, 2, 3, or it might even be 0.5, 1, 1.5, so whatever. But the main thing is that there are gaps or differences or spaces between those values. There are values in between them that cannot be taken on. Continuous are variables that can give any value in a given interval. So height can give you any variable from like 20 inches for a baby all the way up to, I think, 8 foot something is the tallest human alive right now. So these are usually measurements. And you can see any value, it's not just dots on the number line, it's that interval. Any value on that interval can be taken on by the variable. So let's identify some variables here. The color of cars in the teacher's parking lot. That would be categorical. Number of calculators owned by students at your school. Well, that is numerical because it's a number and it is discrete. The zip code of an individual. This one's kind of tricky because it is numbers, but it's actually putting you in a category. You're not counting anything, you're not measuring anything. You're just taking that number code which defines you. They're using numbers to describe it, but they could just very easily say that you're in the city of Madison or the city of Columbus or whatever city rather than using that number code. They could give it a name if they wanted to. It's just they choose to use numbers as the name. The amount of time it takes students to drive to school. Well, this is numerical and it is continuous because it's time. The appraised value of homes in your city. This is also numerical. Is money a count or a measurement? Money is always a tricky one because, well, you can say we can go to, fractions of a penny, or do we just automatically count it at a penny? This is actually discrete numerical because the reason it's discrete is even though we could calculate down to a hundredth or a thousandth or a millionth of a cent, there's a natural rounding point. And that natural rounding point is to the penny, and that's in practical applications, that's where it would always be applied. So we call that discrete because we can count pennies. Classify variables by the number of values. Classify variables by the number of variables in a data set. So suppose that a PE coach records the height of each student in his class. This is an example of a univariate data because only using one variable, the height, not comparing it to any other variables. But suppose the PE coach wants to record height and weight of each student in the class. This is now bivariate. You have two data sets drawn from the same sample or population, you might even consider if you want to consider it that way. But you're drawing two different values and you're comparing those values. You're analyzing them together or against each other. So it describes two characteristics of the population. Now suppose that the PE coach records the height, weight, number of sit-ups that a student can do, and the number of push-ups for each student. This is now multivariate. Multivariate data measures multiple characteristics, more than two characteristics about each item. We're not going to do multivariate data in this course because it's just too complex for an introductory course. Bar chart. So some of the basic graphs. Most of you have seen bar charts before. It is used with categorical data. When it's numerical data, there's a different name for it. How do we construct it? Well, you draw a horizontal line to write the categories on. An axis, in other words, you put your categories down there. And then you're going to do an axis up the side so that we can describe those. The vertical line then is labeled as our scale so that we can record the frequencies. And then, of course, the width of each rectangle, when we draw our bars, we need to try to make sure they're the same width. Because a wider width on a bar like this makes it look bigger, even though it's the exact same height. Your psychology, your mind looks at that and wants to make it bigger. So what to look for in a bar chart? Frequently or infrequently occurring categories. So which categories occur most often? Which ones have the tallest bar? Which ones occur least often? Or they have the shortest bar? So we might collect data about your favorite ice cream flavor. That, of course, is categorical. the dot plot, it is used for small numerical sets of data. In other words, numerical sets of data that fit in a small range. For one, we don't want a dot plot to go from 2 to 315, too large of a range. It has to have a small range, but also a limited number of points. If we have 300 or 400 data points, a dot plot would get pretty cluttered. How do you construct it? Well, you make a number line, a horizontal number line, and mark out your scale and label the numbers. Then for each value in the data set, you just place a dot above the appropriate number on the number line. So let's just say we have values from 5 to 10. If one of our items in our sample gives us an 8, we put a dot above the 8. Another item gives us a value of 6, put a dot above a 6. The next one's an 8, well, we stack the dots up. And we create the dot plot by putting all those values plotted on there that way. Things to look for. Well, they represent representative or typical values. Which one's the tallest? That's the most common value. But how are they shaped? How are they grouped together? Do they squeeze into the middle, or are they spread out kind of flat? And the nature of the distribution. Does it form a bell curve like that? Is it multimodal with 2 humps? Or is it more square like that? And are there unusual values? Is there a little dot way out here somewhere that doesn't seem to fit in? Is there one value that is way off from the others, called outliers? So if we wanted to collect the following data and display on a dot plot, we might use how many body piercings do you have? Going to be from 0 to however many. Shouldn't be a huge range there. And we plot those dots on that number line. So that's the end of Unit 1. We'll pause here for a second and we'll go on to Chapter 2. Moving on into Chapter 2 here. We'll do Chapters 1 and 2 together because they're really kind of the background information together. Chapter 2 also has a lot of vocabulary, and it's very important here that we understand the vocabulary and what each of those vocabulary symbols means. So consider the following headlines which occurred in September 25th of 2009. Spanking lowers a child's IQ. Do you spank? Studies indicate it could lower your kid's IQ. Spanking can lower IQ. So these are different headlines in different papers, all about the same topic. Now, one of the things, if you get into psychology of statistics, the wording of those headlines might trigger different responses in the reader as well. The first one, spanking lowers IQ, that's saying it definitely does it. This one, spanking can lower IQ. So again, just slight little things that trigger the psychology. Smacking hits kids' IQ, a little bit more graphic there. So in this study, 2 groups of children were followed. 4 years, 806 children ages 2 to 4, and 704 children ages 5 to 9. The IQ was measured at the beginning of the study, and again 4 years later, researchers found that the average IQ of children ages 2 to 4 who were not spanked was 5 points higher than those who were spanked, and 2.8 points higher for those children in the 5 to 9 age range. Now, some of these headlines imply that there's a cause, that the spanking is the cause of the lower IQ. In fact, most of these headlines do. But there might be other factors that play into it. It's not the spanking that causes the lower IQ. There might be a third factor that causes both of them. The social scientist studying a rural community wants to determine whether gender and attitudes toward abortion are related. Using a telephone survey, 100 residents are contacted at random and their gender and attitude towards abortion is recorded. Professor might wonder, here's a second example. Professor might wonder what would happen to final test scores if the required lab time for a chemistry course is increased from 3 hours to 6 hours per week. For 100 chemistry students, half were randomly assigned to the 3-hour lab and half to the 6-hour lab. The rest of the course remained exactly the same for the 2 groups. The difference in their final test scores then will be examined. So the first one here, looking at, first of all, let's look at both of these, how the 2 examples differ. But think about How are the groups determined? In the first one, they just randomly chose people in rural communities and called them to ask them. In the second one, they did randomly assign chemistry students to two different labs within the same section, lecture section, so that everything else was held the same. Were any variables controlled? In the first one, no, there were no variables that were controlled. They just surveyed for the information. They just called people, and that's what they ended up with. That is a survey. There's nothing controlled. In the second, or what's called an observational study. In the second one, so an observational study, they're just studying characteristics that already exist, not imposing any of their own conditions on those people. In the second one, they actually did impose different lab times, amounts of lab time on each of the students. They kept everything else the same. They controlled the lecture, they controlled everything else, but they did impose different lab times on them. That makes this an experiment, because they did actually impose conditions on the subjects. So then what did the researchers do? Well, that's exactly it. They assigned them in the second example to those different groups. And in the first one, they just gathered the information that already existed. So which is the experiment and which is the observational study? We've already specified that. So definitions. Observational study. Study in which the researcher observes characteristics of a sample selected from one or more populations. In other words, conditions that already exist. They just observe them and record those observations. An experiment is a study in which the researcher observes a response variable, how a response variable behaves when one or more explanatory variables or factors are manipulated. So in the example in the previous slide, they changed the number of hours of lab time per week. Everything else was controlled, and then the response variable would be then their final score in the class. Do they retain the information better? So a well-designed experiment can result in data that provides evidence for a cause-effect relationship. So just it can provide evidence for it, but notice it didn't say it proves it, because there could always be a third factor that forces the changes in both variables. So you've got to select that explanatory variable very carefully, and then what you're going to measure is the response variable as well. So in the first study, the two groups of children that were followed for 4 years, the IQ and spanking study, does spanking cause a decrease in IQ? Well, there's a relationship between, but we cannot say that there's a cause, because there could be other variables connected to the response. In this case, the response that we're measuring was increase or decrease change in IQ of the groups of children. This is what's called confounding variables. These are variables that are outside of what we're studying, but could have effects on the results, the things that we cannot control. Maybe children that are more likely to be spanked are more likely to come from economically depressed areas. So that might affect IQ. Or maybe nutrition or other things that might be available to households that don't spank that are not there for households that spank. So the definition of a confounding variable, the variable that is related to both group membership and the response variable of interest in the research study. So it's related to both that predictor variable and the response variable. Because observational studies may contain confounding variables, their results cannot be used to show a cause and effect relationship. So in observational study, we're not controlling the variables, we're just watching what happens. We can't predict a cause-effect relationship. Whereas in the experiment, we are changing something. We are changing a thing to see if something else changes. There, it's a little bit easier to establish that cause and effect. Observational studies can be generalized to the population if the sample is randomly selected from the population of interest, but they cannot show a cause and effect relationship. Well-designed experiments can show a cause and effect relationship, but cannot be generalized to the population if the groups are volunteers or are not randomly assigned. This is one of the difficulties in an observational study and in an experiment is volunteers. You do a survey, you can't force somebody to respond to your survey. Well, that makes them volunteer, which means we can't do a whole lot with it. It has to be randomly selected. If they're volunteers, well, then they have choice, and that's no longer random. Well-designed experiment, the population has to be randomly selected. The sample, I should say, has to be randomly selected from the population. And then there's some ethics issues there. Can you force somebody to participate in this? The chemistry example, again, not randomly, it was one section and they randomly selected, but we can't generalize that to other sections of chemistry because they didn't have a chance to be in that sample. So it's not truly a random sample of all the sections of chemistry. It's only a random sample of that section of the chemistry course. So sampling, we talked about this a little bit in chapter 1, and there's going to be a big deal, so let's talk about it. Census versus sample. Remember, a census was gathering information from the entire population. A sample is a smaller group from that population, that subset of the population. It makes it easier to study. Why would we want to take a sample rather than perform a census? Well, one is if the measurement requires destroying the item, sometimes referred to as destructive testing. In industrial and manufacturing, this happens quite a bit. You have a part that you want to know how much force it can withstand, how much tensioning, how much load it can handle. But you put it in a machine and you apply force to it and you increase that force more and more until it breaks. And you measure how much force it took to break it. And that critical force, the fracture force, allows you to predict if that part would have likely held up under its normal conditions. Well, you can't test every part because when you test it, it's destroyed. And then you wouldn't have any parts left to sell or use. So measuring how long batteries last is an example. You use a battery and you wear it down until it's no good. Well, you can't test every battery or you won't have any left that are charged up to sell. Safety ratings on cars. Again, you can't crash every car into the wall. It might be difficult to find the entire population. Let's look at like presidential elections or even any national election. The population you're looking at isn't all voters. The population you're looking at is the people who will vote. Those that, even though they're registered voters, but they're never going to vote, we don't care what their opinion is because they're not going to affect the results. But some people don't know if they're going to vote or not. Some people might be determined that they are going to vote, but the day of the election, something happens, they're held over late at work, or they get a flat tire or whatever, and they don't make it there to vote. So it's difficult to find, even define what the population is, much less find every member of the population. So you want to measure the length of the fish in a lake. You can't catch every fish and measure them. Limited resources. This usually comes down to time and money. We don't have the time to access everyone. We don't have the money to pay for the time for people to access everyone. And this is our most common reason for taking a sample. It's the most common reason for just about anything. Methods of selecting a random sample then. Now that we know why we take a sample, how we select that is a big deal. Now, one of the things is sample size. You need a big enough sample so that it can be representative of the population, but not so big that it's difficult to gather the data from. So here we suppose a local high school has 2,000 students. We want to survey 100 students about the current cell phone policy. Sample of students can be selected by putting each student's name individual on identical slips of paper, placing them in a large container, and after mixing them well, randomly selecting 100 names. This is the example of a simple random sample. It is the best kind of sample to take. Simple random sample length is literally putting all the names in the hat. Simple random samples, when you determine a sample size, in this case we determine we're going to have a sample of 100 students, and every possible sample of that size has a chance of being chosen. So in this case, every possible sample, every different sample with 100 people in it has a chance of being chosen. So it is possible for all 100 students to be seniors, all 100 students to be male or female, all 100 students to be in the same homeroom. Not necessarily desirable, but it's possible that those quirks could occur in our sample because it's a simple random sample. There are other sampling techniques that are random, but not simple random. So simple random sample, every possible sample of that size has a chance to be chosen. Just plain random just means every item has an equal chance of being chosen. Every item in the population has an equal chance of being in the sample, but not every possible sample of that size. So a simple random sample does not guarantee that the sample is representative of the population. It doesn't guarantee it's representative, but it is necessary for many of our statistical analysis techniques that we have a simple random sample. Because what our techniques are doing is taking into account that possibility that it is not representative. Now, the word representative we haven't really defined yet. The word representative just means that the characteristics of the sample very closely resemble the characteristics of the population. The mean is a perfectly represented sample. The sample mean would be the same as the population mean and all that. Another way to select a simple random sample is to create a list of all the students, called the sampling frame, and then electronically go about it. So the sampling frame is a list of all the students or individuals of the population. Number each of those students 1 through 2,000, assign them a number, and then randomly select numbers using either a number table or a random number generator of some sort, calculator or Excel or some other computer software. So the following is part of the random digit table found in the back of your textbook. You've got these rows and you got these random digits. Since our students are numbered 1 to 2,000, we will select 4-digit numbers from the table. So to do that, you just select 4 digits in a row. If the number is not within 1 to 2,000, we will ignore it. So if it's more than 2,000, we ignore the number. So if we're using row 6, first one in is 938. 7,679 is more than 2,000. I'm not going to use it. This one's going to be more than 2,000. I'm not going to use it. So you can see that one isn't used because it's more than 2,000. That one not going to be used because it's more than 2,000. More than 2,000. More than 2,000. That one's 220. That one we'll use. 4,000. That's more. Too big. 1,947. That one we'll use. That one's too big. Too big. Too big. 1,231. That's in our range. We'll use it. 1,800. We'll use it. 4,000 is too big. 8,000 is too big. So you can see it can be kind of tedious to select the numbers to select the sample. We'll go through a large portion of the table going this way, but you'd eventually select that sample. So we continue until we selected 100 numbers, and then we go in that list and select the students that corresponded to those numbers in our list. So most often sampling is done without replacement. What that means is you draw a student out, or a student's name out of the hat or the box, or their number from the random number tables. We can't choose that same person again. They're not going to be repeated. So what that means, once that student is selected, that individual is selected, it's not put back into the population to be selected again. Sampling without replacement with replacement allows an object to possibly be selected again in a future selection. A big example of this would be marbles in a box. When we talk about probability, we'll talk more about with replacement and without replacement. So although sampling with and without replacement are different, they can be treated as the same if the sample size is small compared to the population size. So if we have a large enough population, it really doesn't matter if we're sampling with or without replacement, because whether we put the person back into the sample or into the population or not does not significantly change the probability of drawing out of selecting the next person. So methods of selecting just random samples, not simple random samples. So instead of a simple random sample to answer a survey about the cell phone policy, suppose we take 4 simple random samples of size 25 from each grade level, freshman, sophomore, junior, senior. This is called a stratified random sample. It is random because every student has, assuming that the 4 classes are about the same size, each student has about the same chance of being in the sample. So it is random, it's stratified random, but it is not simple random because it's not possible to have a sample that's all seniors or all freshmen or any of that. It guarantees equal representation for each grade level. So the population is divided into non-overlapping subgroups. In this case, it was grade levels. Those subgroups are called strata. And then we randomly select proportionately from each strata. If they're, the strata have to have some defining characteristic that separates them from the other strata. That makes sense. We can't just be randomly breaking them down into subgroups. Then the simple random samples are selected from each stratum, from each of those subgroups. In this case, it was from each grade level. Sometimes it's easier to implement, and it's often more cost effective than doing the whole simple random sample. It takes a lot of work to write down all the names, throw them in a box, and draw them out. Here, though, we can just work at sampling populations of 500 each, if assuming that 1/4 of each of the 2,000 was in each grade level. Sometimes it allows more accurate inferences. The reason it allows more accurate inferences, of course, is we know that every one of those subgroups is represented equally in the sample or proportionately in the sample. Another method is we might divide the population into groups again, but then select whole groups to sample. In this case, the population is divided into groups by what classroom they're in at a certain time of day. In this case, they're specifying second period. And then just randomly selecting 5 classrooms and going to those classrooms. That's called a cluster sample, because you're dividing the population into clusters and then picking whole clusters to survey. Now, this is cost effective and time effective because you don't have to track down all these randomly selected students. You can just go to one classroom, survey those students, and go to the next one. So you get a large amount of data with minimal effort. So as we said, the population is divided into those clusters, and we randomly select clusters to take. The clusters don't have to have don't have to be divided up by a special characteristic. It just has to be a convenient cluster. Most of the time based on location or some other characteristic defines how easy it is to collect data from. So then we randomly select whole clusters to survey. So as we said, cluster sample is often easier and more cost effective just because you get more data in one location. Next method, let's say that we randomly select a starting point. In this case, we'll randomly select a number between 1 and 20 using the alphabetical list of all the students at the school. And then once we've done that, then we choose, once we've chosen that first number, then we take every 20th student on the list. So if our first number is 13, then we would take the student number 13 on the list, student 33, 53, 73, and so on. We randomly selected the starting point, and then the system takes over from there. That's why it's called systematic random sampling. Again, every student has an equal chance of being chosen, 1 in 20, based on what that first number is chosen, but it's not simple random because not every possible sample of size 100 could be chosen. We can't take all 100 students in the A's or anything like that. So characteristics of simple or systematic random sampling, I should say. Again, we start out, we pick that random starting point. Once we've picked that random starting point, then we select every kth item in the sequence. If we need a sample size of a certain size, we divide the size of the population by the size of that sample to get k. So in this sample, k was 20, because we had 2,000 students in the school and we wanted a sample of 100, so 2,000 divided by 100 gave us 20. That's why we selected a student from 1 to k, from 1 to 20, as a starting point, and then we went every 20th one or every kth one after that. This method works reasonably well as long as there are no repeating patterns in the population list. In other words, large families, so that the names would be all grouped together. Well, now, that could be an issue because you've got a pattern within the list, and that system is not accounting for that pattern within the list. So identifying the sampling design that we want to use. The Educational Testing Service, ETS, needed a sample of colleges. The ETS first divided all colleges into groups of similar types: small school, public school, medium, private, and so on. Then randomly selected 3 colleges from each group. Well, since they divided into groups, now there's 2 possibilities when you're dividing the population into groups. It could either be a cluster sample or a stratified sample. So we asked, do these groups, are they grouped by convenience or location, or are they grouped because they have something in common? Well, small public schools, those all have that trait in common. They're all public and they're small. Medium private schools are medium-sized and private. They have traits in common. This is going to be a stratified sample. To confirm that, a cluster sample, we would have selected whole groups to survey. Here, we just selected 3 colleges from within each group. So it's stratified. Identify this one. A county commissioner wants to survey people in her district to determine their opinions on a particular law up for adoption. She decides to randomly select blocks in her district and then survey all that live on each block. So again, we're dividing the population, in this case, the commissioner's district, into groups, but those groups are not selected by a common characteristic. They're selected by location, ease of access. So this is going to be a cluster sample. When you actually have to travel to homes, a cluster sample is usually very popular because you can go to that one block and just walk around the block and survey all the homes rather than having to get in your car, drive to the next randomly selected place. So you're jumping all around the city. A local restaurant manager wants to survey customers about the service they receive. Each night, the manager randomly chooses a number between 1 and 10 and then selects that customer and then every 10th customer after that. Well, this is obviously a systematic sample. They choose a starting point and the system chooses all the ones from there. So let's consider this following example here. In 1936, Franklin Delano Roosevelt had been president for 1 term. The magazine, The Literary Digest, predicted that Alf Landon would beat FDR in that year's election by 57 to 43%. The Digest mailed 10 million questionnaires, the names drawn from a list of automobile and telephone owners, and over 2.3 million responded. It's a huge sample. 2.3 million is a huge sample. Now, there's a couple of issues here. One is they were drawn from automobile and telephone lists. At that time, it wasn't uncommon for people not to own a car or a telephone. There's a large section of the population that's left out. Also, FDR was strongly supported by the people that were unemployed or lower income. Well, those would be the people that would be more likely not to have a phone or a car. Second, 10 million were sent out, only 2.3 million responded. That's less than 1/4 response rate. So it's a voluntary response survey. Excuse me. The people that are more likely to respond to a survey are the ones that are more likely to have strong feelings. So let's continue on here. At the same time, a young man named George Gallup sampled only 50,000 people and predicted that Roosevelt would win. Gallup's prediction was ridiculed as naive. After all, one second. You can come on in. After all, the Digest had predicted the winner in every election since 1916 and had based its predictions on the largest response of any poll in history. But Roosevelt did win by 62% of the vote. The size of the Digest error was staggering. So what caused that error? So this is a classic example of how bias affects the results of a sample. Bias is the tendency of a sample to differ from the population it's drawn from in some systematic way. A selection bias is the big one. And this is the way we select the sample. It maybe doesn't create the bias, but it increases the chances of that bias existing. Suppose you take a sample of randomly selecting names from the phone book. Some groups will not have the opportunity to be selected because they don't have a phone, so they wouldn't be in the phone book. Again, we talked about the high income families being the ones most likely to have phone numbers, or the lower income families not having phones, but higher income families most likely to have unlisted phone numbers, so they wouldn't be in the book. There we go, people without phone numbers, typically the low income families. So if you're using the phone book, you're only getting that middle range of middle income families. And now, of course, in the modern times, people with only cell phones usually would not be listed in the phone book. So that tends to be younger adults that only have cell phones and don't have a landline anymore. So you'd be excluding that group from possibly being in your sample. So like I said, this occurs when the method of sampling systematically excludes a certain portion of the population of interest. We call that undercoverage. That portion is undercovered in our sample. It may also occur if we use voluntary or self-selected samples. That's where they decide they're going to respond. Again, we talked about it. They only respond if they have some strong feeling or some reason, motivation to be part of it. So suppose we decide to survey only the students in our statistics class. Why might that cause bias in a survey? Well, because they're exposed to me, and being in my class, certain opinions might have rubbed off, or certain things I've taught them might have affected their thought process. That's called a convenience sample. They're easily available, but it's not an accurate or reasonable representation of the whole population. Not representative of our population of interest. Therefore, the results cannot be generalized to the whole population. What I've really done is I've limited my population to my own class, even though I said my population was all students. So it can't be generalized to a population that's not represented by that sample. Again, when we rely totally on voluntary responses, this type of thing can occur because maybe they're the people who had time to respond for some reason, or they were easy for us to get the information to, so they actually got it. The other people, we tried to send them the information and it didn't get to them. So an example would be the surveys in a magazine that ask readers to mail in the survey. Well, first of all, they have to be people that subscribe to that magazine, and there's typically very narrow groups of people that subscribe to certain magazines. An example might be call-in shows like American Idol. Well, first of all, they have to subscribe to the magazine, and then they have to have an interest in those shows. If they don't have an interest in those shows, they're not going to respond to that survey. So those self-selected surveys, voluntary response surveys, tend to be more strongly in favor of it because only the people that favor that topic will typically take the time to respond. Then there's a measurement or response bias. This occurs when the method of observation or the method of measurement tends to produce values that are systematically different from the true values of the population. So an improperly calibrated instrument or a scale used to weigh items, that can cause a bias. It's the measurement instrument itself that's not calibrated. We're not measuring accurately. Tendencies of people not to be completely honest. So if you're asking about use of illegal drugs or something like that, people might not want to say, yeah, I do. They might be more likely to lie to you to protect their own legal interests. Suppose we want to survey high school students on drug abuse, and we use the uniformed police officer to do the interview. Most students are not going to admit to a uniformed police officer that they abuse drugs. Appearance or behavior of the person asking the question. So again, the police officer answering a question about committing crimes might be a little different. A non-threatening person, someone their own age, and in many cases is much more useful, might be more likely to get an honest response out of that participant. People are asked if they can trust men with mustaches. but the interviewer is a man with a mustache. Well, you're not going to say, nope, can't trust you. You're going to try to appease. There's a human tendency to appease the person who's in front of you at that moment. Questions in the survey are worded in such a way that tend to influence the response. A great example of this that I can think of is wanting to increase funding for school lunches. If you say, would you be in favor of a 2% increase in your property taxes to fund better school lunches? First thing you saw there was increase in property taxes. You probably didn't even hear the rest of it or read the rest of it. But if you word it a different way is, if it meant that our young people could have better lunches at school, would you be willing to pay a few percent more in taxes? Calling upon that emotional item first, the feeding our kids better, is more likely to get a positive response. Their example here, the Gallup survey sponsored by the American Paper Institute, included the following question. It is estimated that disposable diapers accounts for less than 2% of the trash in landfills. In contrast, beverage containers, third-class mail, and yard waste are estimated to account for 21% of trash in landfills. Given this, in your opinion, would it be fair to tax or ban disposable diapers? Well, they're presenting you with an argument towards one side of the question, then they're giving you the question. Our argument is, hey, diapers are less than 2% of the waste, and other stuff is way more. So do you think it's fair to tax diapers? So they're giving you information that's going to sway your opinion before they even ask the question. A non-response. So again, you can't force people to answer a survey. Phone rings, you answer hello, the person says, do you have time for a survey? And you hang up. That's a non-response. So the responses are obtained from individuals that are selected for inclusion, but they just don't respond. They were selected and you just didn't get an answer from them. And those people who don't respond have a tendency to answer, and usually in a certain way or a common way. To minimize the non-response bias, it is critical that serious efforts are made to follow up with those individuals who did not respond to the initial question. Again, you still can't force them to respond. So how might this be done? Well, the people are chosen by the researchers but refuse to respond. It's not self-selected. That is a voluntary response. So there's a difference between self-selected and voluntary response. Self-selected is like the magazine. You had the survey in the magazine. They're reading it. They decided they wanted to fill it out and send it out. They weren't selected by anybody else. They were self-selected. Well, the ones where you call them up and they hang up on you, you selected them. So they're not self-selected, but you can't force them to respond. They either respond voluntarily or they don't. That's the voluntary response. So identify the potential source of bias. Before the presidential election of 1936, FDR against Republican ALF Landon, the magazine Literary Digest predicted Landon winning the election by a 3-2 victory. A survey of 2.3 million people, George Gallup surveyed only 50,000 and predicted that Roosevelt could win or would win. The Digest survey came from magazine subscribers, car owners, and telephone directories. Well, again, there it is the under coverage. We're not choosing those people that don't have phones or cars. Suppose that you want to estimate the total amount of money spent by students on textbooks each semester at a local college. You collect register receipts for students as they leave the bookstore during lunch one day. Well, there's under coverage here as well because students that weren't in the bookstore at that time wouldn't be part of the sample. Students who worked at that time of day or had class and couldn't get to the bookstore would not be included. They'd be excluded. They'd be undercovered. But it's also a convenience sample. You showed up and just did it during this period of time. It was convenient for you, an easy way to collect that data. To find the average value of a home in Plano, one averages the price of homes that are listed for sale with a realtor. Well, again, under coverage, homes that are not up for sale are not able to be in that sample, or homes that are up for private sale. Let's talk about comparative experiments. Remember, experiments are where you create a condition and randomly assign people to those conditions and see what happens. So suppose we are interested in determining the effect of room temperature on performance in a first semester calculus exam. So we perform an experiment. What variable will be measured? Well, the variable that will be measured is the performance on calculus exam. This is called the response variable. That's the variable that is hopefully reacting to the one that we control. What variable will explain the result of the calculus exam? Well, this is the one that we alter, we control, the predictor variable. And that is the room temperature. The explanatory variable that explains the cause, hopefully, of it. Remember, we can't always assume that cause-effect relationship, but we're choosing it in such a way that we're hoping that that explanatory variable explains the changes in that reaction variable, our predictor variable. Room temperature, experiment continued. We decide to use two temperature settings, 65 degrees and 75 degrees. The 65 degrees might be a little chilly, and 75 is actually probably a little warm. How many treatments would this experiment have? It has two, 65 degrees and 75 degrees. Experimental condition or treatment is any different combination of the explanatory variables. So two treatments, and there are the two temperature settings. Suppose we have 10 sections of first semester calculus that have agreed to participate in our study. On who or what will we impose the treatments? Well, on those students that are taking the test. We have to divide them into those two groups. So the 10 sections are the ones we're impose the treatments on. So these are the subjects or the experimental units. How would we determine which sections would be in the rooms with the temperature set at 65 and which in the 75? We would have to do a random sample, simple random sample. So we'd assign them to that, probably throw them in a box and draw 5 of them out. Those would be the 65 degrees and the other 5 would be the 75 degrees. So it's very important that we do that random assignment. Otherwise, we could end up subconsciously having a bias and picking the students that are from a professor that's known to have higher grades in one temperature or one condition and the others in a different condition. So to randomly assign the 10 sections of first semester calculus to the two treatment groups, we would first number the classes 1 through 10 and then assign them. Place them in the hat and mix them well and then draw them out. The first 5 selected get the 65 degrees. The other 5 get the 75 degrees. So the first one draws student 9, section 9, 7, 5, 8, and 3. So those 5 sections take their test at 65 degrees. The rest of them are at 75 degrees. Notice there are 5 assigned to each treatment. And of course, none are assigned to both treatments because they have to be separated. This is called replication. Each treatment is being tested more than once. Multiple observations for each treatment. Why is replication an important trait of a well-designed experiment? Well, you can't just test one student at 65 and one student at 75 because there's a good random chance that one of those students has more ability than the other. Even if it's just one section, one group of students, there's a good chance that maybe the professor for that group did a better job of explaining it. So it might not be the temperature that causes the difference. It might be some other factor. So that replication helps to limit the effects of those potentially confounding variables. Are there other variables that could affect the response? Yep, the professor that teaches the class could very well be a confounding variable. Time of day, if they take, what time of day their exam is scheduled. Some students perform better in the morning and some perform better in the afternoon. Right after lunch is usually a bad time for any exam. We said the instructor. The textbook. Hopefully they're all using the same textbook. If not, that's an issue. They're not necessarily being tested under the same conditions. Ability levels of the students. Were they students randomly assigned to sections of calculus, or were students with, it was one of those sections a gifted section or an honors section, or was one a section that was designed for students who struggle or non-math majors or anything like that? We have to take those things into account. So these are extraneous variables. They're variables outside of our control that can have an effect on that response, but we can't measure their effect. In an experiment, these extraneous variables need to be controlled. So control means we need to keep them constant or to limit their effect on our response. Direct control is holding these variables constant so that their effects are not confounded with those of the experimental condition. So we do something to make sure that they are equal or constant. Can the experimenter control the instructor? Well, yeah, we could choose sections that are all taught by the same instructor, or instructors that have similar student reviews each semester, or instructors that have traditionally had close to the same average grade on that final exam. So what about variables like time of day and stuff like that they can't control? Well, I suppose they could just select all students that take morning exams or whatever, but you can't control the ability levels of the students. These are the confounding ones. They affect the response, but we can't do anything to limit that effect. Suppose that there were 5 instructors who taught the first semester calculus. We do not have direct control over this variable. However, we could have each instructor teach 2 sections, and then one section's at 65, the other's at 75. Randomly select which goes where, but make sure that so there would be a stratified sample. You're choosing one from each instructor rather than just 5 from the general set of 10. This is a block sample, randomized block sample. You have the blocks, in other words, each instructor, and you're choosing randomly from within each block. What about extraneous variables that we cannot control directly or that we cannot even account for or didn't even think of? Randomly assigning items from the population into samples usually evenly spreads out those variables so that they cancel each other out. We can't control them, but we can kind of spread their effect out through the data so it doesn't have any significant effect on one group or another. We would expect them to affect each group in the same way so that their effects cancel out. Would the student in each section of calculus know which treatment group they were assigned? Now, there's a question. It's called a blind study. Do you know what treatment you're getting? If students believe they work better in cold temperatures than warm temperatures, and you tell them that they're going to be in the warm temperature, subconsciously they might perform poorly because they think they're going to perform poorly in that higher temperature. So if the students knew about the experiment, they would probably know which treatment they were in because they could feel the temperature difference. So there's an ethics issue here, but we would prefer not to tell them so they don't know that there's an experiment even going on. It's called a blind experiment or a single blind because the students don't know, but the people working with them would know. This experiment is probably not blinded because the students would know that there was a difference. Double-blind experiment, not only do the subjects not know, but the people who are measuring or evaluating the subjects don't know which group they're in. That's to avoid any observational biases by the observer. In a room temperature experiment, we only have 2 treatment groups, 65 and 75. We do not have a control group. A control group would have no treatment at all. They'd be under standard conditions with no altered treatment. Here we altered the treatment for both of them. One was cold, one was hotter than normal. We should have a group that's right in the middle at 70 degrees or whatever our standard thermostat setting is. The use of a control group allows the experimenter to assess how the response variable behaves when the treatment is not used. So maybe the ones tested at 65 score exactly the same as those tested at 70. The ones at 75 test lower. So then we could possibly conclude that lowering the temperature doesn't have much effect, but raising the temperature does decrease performance. The control group also provides a baseline in which to compare the other groups like we just saw. Consider Anna, a waitress. She decides to perform an experiment to determine if writing thank you on her receipts increases her tip percentage. She plans on having two groups. On one group, she'll write thank you on the receipt, and on the other group, she will not write thank you. Which of these is the control group? Well, the control group would be the ones with no treatment, the ones that she would not write thank you. Suppose we want to test an herbal supplement to determine if it aided in weight loss. Why would it not be beneficial to have two groups in this experiment? One that takes the supplement and a control group that takes nothing. Well, there's too many other things that could get in the way. It's not just taking the herbal supplements, what's their diet, what's their exercise level, and other stuff that determine it. So it really isn't going to be the herbal supplement isn't probably going to be the dominant variable here. What could be done to remedy this problem? Well, you could have a group come in and divide it into two groups, and each group gets a set meal plan, set amount of physical activity every day, and so on, controlling all those other characteristics could have that confounding effect. So give one group the supplement and the other group a pill that is the same size, color, and taste, but contains no active ingredient. This is the placebo effect of the group getting the pill might think they're going to lose weight, so they do, the other group doesn't. So there is that placebo effect. So they're given the identical treatment even though there's no active ingredient there that could have any effects on them. And their random assignment means we spread out the possible potential for confounding variables. Blocking helps us to guarantee that the two different treatments are similar in characteristics. Direct control means that we can directly keep that variable from being different from one subject to another. Experimental design. Completely randomized design means that the experimental units are assigned at random to treatments, or that the treatments are assigned at random to different trials. So we have our experimental units, and some go to treatment A, some go to treatment B. So we can measure the response. So then we measure those responses and we compare the treatments. So let's look at two examples of completely randomized experiments. Farm product manufacturer wants to determine if the yield of a crop is different when the soil is treated with different types of fertilizer. 15 similar plots, so the soil being the same seeds and everything else, but are fertilized differently. At the end of the growing season, the mean yield from each plot is compared. So the plots are the different experimental units here. The factors are, everything else is controlled, so it is the fertilizer. As long as they're in a type of area where they're going to get the same amount of rain, they're close enough together and stuff like that, same amount of rain, same amount of sun and stuff like that. Response variable is going to be the yield. How many treatments? Well, there's 15 different plots, it says. Oops, sorry. 15 similar plots, 3 different types of fertilizer. So 3 different treatments. Why is the same type of seed used in all 15 plots? Well, to make sure that the effects are the same. We're having multiple trials of each type, so that takes out any slight differences that might be there from each location. Potential extraneous variables. Drainage of water from outside the plot onto the plot, or amount of sun if there's trees around it blocking the sun, all sorts of things, and slight differences in the water or in the soil. Does this experiment have a placebo effect? No, it doesn't have a placebo because the plants aren't conscious, so they don't know whether they're getting a treatment or not. So it's not needed. Second experiment, a consumer group wants to test cake pans to see which works best. Bakes the most evenly, so aluminum, glass, or plastic, and both gas and electric ovens. There are 30 boxes of cake mix used for the experiment. So the units here are the different cake mixes. We're testing them out. The factors here are the different types of pans. And then, of course, the type of oven, electric or gas. The response variable is how evenly it cooks. The treatments, well, aluminum pan and electric oven, aluminum pan and gas oven, each type of pan and each type of oven. Describe how to randomly assign the cake mixes to the treatment so that there is an even number of treatments. Well, personally, I would use the same cake mix for all of them, but you just take the treatments and put them on a list, and then for each cake mix, you reach in the thing and draw out a treatment. That's what that cake mix gets used for. And there we go. That's how they're describing them, 1 through 30. This is just one way that you could randomize it. There are a lot of other ways that it could be done. We could roll a die for each box, assign it to treatment 1 or 2, then flip a coin, decide which type of oven it's used in. All sorts of different ways we could do it. The big thing is we got to make sure that they're spread out. It's hard to keep one from having all of them in a gas oven if we do the random treatments. So we got to try to make sure that it's somehow split up evenly. So that's why we use a randomized block design. The units are blocked into groups, homogeneous groups, so then they're randomly assigned to treatments. There's our experimental unit. Block 1, block 2. Block 1, part of them are assigned to treatment A and treatment B. Block 2, part are assigned to each treatment. And then, of course, we take the measurements and compare. Unit should be blocked on a variable that affects the response. So like in the calculus experiment, the professor. So we know that they had the similar professor, so that we can divide them into treatments, knowing that they had similar backgrounds. Can the experimenter directly control the types of soil? No, they cannot. They can test the soil and select plots that are similar, but they can't directly change the soil itself. What can be done to account for this variable? Well, you could prep the plots. It would take years of fertilizing and prepping the plots ahead of time to get them the same, or you could just sample several plots and pick the 15 that are closest in soil composition. Or as they said here, they could block up by type of land. Soil types, make sure that if you got 3 that are this soil type, each of them gets 1 of the different types of fertilizer. How to create blocks? Well, again, by soil type. You test the soil and the ones that are most similar, or maybe the ones that are closest to a water source, drainage types or whatever, block them up by that and divide them evenly amongst the treatments. Another different way of using the 10 blocks to divide them up as well. And then again, you could number them and block them out that way. Experimental design. We do matched pairs. So you have pairs that it's logical to think that 2 of them are going to respond similarly to treatments. So you make sure that one gets in one treatment and the other gets in the other treatment, so that more accurately describes the effects of the treatments because they're similar to begin with. Or the block, just kind of the same thing. It's rather than matching pairs, you're matching groups and then dividing them up evenly. This is a third example that I'll let you go through on your own. You can pause this and read through it. You can see they use that block example. So the only way to show a cause-effect relationship is a well-designed and well-controlled experiment. If you don't control it well, you cannot assume that cause and effect relationship. And you can't extrapolate it to a larger population. That's it for chapter 2. That's all of our stuff for week 1. Hopefully this helps you along the way. We will discuss more when we have our online office hours.